それでは次の講演を始めさせていただきます。続いては、リフレックス、パーサーをくれ、トークンジェネレーターを上げるからと題しまして、パオロ・モンテセルさんからご紹介をいただきます。パオロさんはイタリアのセキュリティ研究エンジニア、バイナリ変換、リバースエンジニアリング、応用機械学習に焦点を当てた会社に勤務。彼は CTF プレイヤーでもあり、デフコン CTF27 では5位に入賞した経験を持ちます。パオロさんからは今回のテーマについて動画をいただいております。また、ご覧いただきましたら、皆様からのご質問を直接ご本人にお聞きできますので、ぜひ動画をまずはご覧ください。
皆さん、こんにちは。私はパウロ・モンテセルと申します。今日はリフレックスについて話したいと思います。5年前にブルカヌスというプロジェクトのおかげで日本に1年間働いて住んでました。その時、日本語を少し習いました。ですけれども、日本語にまだあまり上手ではないので、これから英語で続けたいと思います。ありがとうございます。Okay, so let's start in English now. I'm Paolo Montesel, and I'm going to talk about Reflex, a tool that I built that takes a parser in a binary and gives you a token generator. About myself, I'm a CTF player with Macaroni, and I'm currently working as a contractor at Revenge SRLS, an Italian company that's creating an LLVM-based decompiler. I'm a security research engineer, and I mainly work on dynamic binary translation and machine learning for reverse engineering. I'm also interested in reverse engineering. I'm a reverse engineer, and full system fuzzing and obfuscation. Okay, so the presentation is going to start with a brief introduction about the tool, how it was born, and why it's useful. And then we're going to talk about the technical details. So let's start with what's Reflex. Reflex is a tool that is able to extract valid tokens and regular expressions from a GNU Bison generated parser. Okay, the scenario in which you might want to use something like this is you are looking at a binary that implements a custom language of some kind for which you don't have documentation, or maybe you have it but it's not well written, and maybe you don't have, or maybe you have few valid samples, and you might not be able to instrument the target efficiently. For example, let's think about firmware. How was it born? Well, last year the NSA released Ghidra, an open source decompiler, but at the beginning the source code was not available. Anyway, this unofficial Ghidra account started screaming that the sources were available in the zip files in the binary distribution, which was true, but only for the Java part. So I told them that, yeah, the compiler part, which is the most interesting, is not available yet. And they replied in a not so friendly way, so I decided to basically get my revenge against the NSA. So I wrote this tool that took this part of the Ghidra decompiler, which is called slave, and is able to extract the tokens for that binary. That allowed me, after some 10 minutes in AFL, to find an integer underflow, which is still there in the current version, but it's not exploitable. But anyway, I had my victory against the NSA. Then again, in August last year, we were at DEF CON CTF with Macaroni, and we were able to use my tool to gain advantage over the other teams because one of the challenges was using Bison. Then I quit my PhD, and here we are at Code Blue. So why you should be interested in Reflex? Well, analyzing parsers in binaries is very time consuming. Most of the time, the code is not manually written, but is auto-generated from some kind of specification. And in the case of language parsers, you often have finite state machines that are encoded either as table-based parsers, like Flex and Bison, or control flow graph based parsers. So the table-based parser are basically a bunch of tables that encode a finite state machine plus a generic matching function, which in this case is called YYLX. While in the other cases, the finite state machine is encoded in the code itself, like you can see here. So how do you get the tokens out of a binary? Well, most of the literature around this subject is centered on dynamic approaches, and they assume that the target can be executed, and so that you can also get coverage information out of some randomly generated input. But these approaches fail on table-based parsers because the code that does the matching on the input is the generic function, and it's always the same, so you don't get valuable coverage out of it. They also usually require a large corpus of valid inputs, so you can try to guess the format or make strong assumption on program behavior, for example, an early exit in case of error. Some papers go as far as saying that table-based parsers are not interesting because if you have a table-based parser, you have the grammar, but what about closed source software, right? These are some popular open source parser generators rather. We're gonna focus on Bison and Flex, specifically on Flex, which is the tokenizer. You can find Bison in many places. For example, I found it in VxWorks, which is a very popular commercial real-time operating system that's also used in PLCs. You can find Bison inside AutoIT, which is a Windows automation software, or you can find it in Zixer routers, for example. You can probably find it somewhere also in Bosch India software, because they were asking about commercial licensing stuff on the mailing list. So if you have any information, I would like to know. And let's get to the technical part. But then again, I need to give a refresher on parser theory, very simple. And then we're going to talk about how we can identify the information we need in a binary in order to recover the finite state machine. And from the finite state machine, we're able to recover the regular expressions and generate valid tokens out of them. So very simple and too simple maybe parser theory. As I said earlier, a developer usually writes some kind of specification. In the case of language parsers, usually it's a grammar of some kind. And then there is a tool that takes the grammar and outputs two pieces of code. One is the lexer and one is the parser, and they work together. The lexer is the first part that touches the input, and it's basically a piece of code that tokenizes the input. And so you get, as an input, you get a stream of bytes, and as an output, you get a stream of tokens. Then comes the parser, which takes the tokens and put them in some structured representation. Most of the times, especially for language parsers, it's some kind of abstract syntax tree, as the one you can see in the example. But how do we get, how does Flex work, and how does it get to the finite state machine? Well, what you do when you write a lexer using Flex is you define a set of rules, these ones, that are made like this. On the left, you have a regular expression like this one, and on the right, you have some kind of token ID. So you can see here, I put an enum to give a symbolic name to the tokens. So for the finest two, Flex takes this and generates some code that uses this finite state machine. For those of you who are not familiar with finite state machines, so basically they are some kind of graphs. And you have a starting state in this case, which is 1. This is the label. The label is the ID of the state. State or node is the same. And then you have some state with a double circle. That means that if from the starting state we're able to reach, for example, this state with a double circle, the current input is a valid token. So if we get D, then E, then F, we get a valid token in state 4 of type define, okay? And this is the same for the others. But then Flex doesn't only generate this finite state machine for performance reason and for historical reason. Flex compresses this finite state machine using some techniques from the Dragon book, which is a very popular compiler book. And what you get as an output is a bunch of tables which are equivalent to the graph on the left, plus this generic matching function, which is in this case is called YYLEX. And keep in mind these tables because we're going to see them again. Okay, so what do we need to extract the finite state machine from a binary? Well, it turns out that we just need the tables and the size of their elements, plus this integer constant that we find in the function code, okay? Once we have that, we can recover the original finite state machine. And the steps needed to do that is, well, first you need to find the matching function. Then you need to find the tables, and we're going to do it in a simple way using some data flow analysis. Then we can infer the element size of the tables from the memory accesses in the code. And finally, we can interpret the tables so that we recover the original finite state machine. So the first part, to identify the table, we can start with Ghidra, okay? We load the binary and we let it analyze it, and then we extract the data flow graph for the matching function. I'm not going to talk about how you find the matching function because it's orthogonal to this work. There are many papers about function recognition. You can look them up. Okay, so we have the data flow graph here. It gets simplified by our tool, and then we put it inside Apache Tinkerpop. And Apache Tinkerpop is a GraphDB, an open source GraphDB, which uses Gremlin as a query language. So you can write query on the graph. So let's see an example of a query. Let's say we want to match this code. This is taken from the matching function. Of course, when you analyze a target, this is going to be the compiled code, so it's not going to be as nice, and you might not have symbols. But just to explain, I'm going to show the source code. Let's say we want to identify YYDef. So what we can do is we're going to look in the data flow all the places in which we have a variable that ends up being used as an index inside the table, which is a global variable itself, and the result is stored in the same variable. And then the data flow reaches this comparison with a constant, and then we have a conditional jump to reach this part of the code. And you can represent this in this kind of way. This is a simplified version of what you might write in Gremlin. So you write, okay, give me every places in which there are two global variables that are added together, and then they are used as a pointer that flows into, that gets the reference, and then flows into a comparison operator that flows into a conditional jump. Of course, this might get you duplicates, but if you piece together many small queries like this, you are able to recover the tables, the table names and their size, and also like the magic value that we want to find. Okay, so how do we get from the table that we found using the data flow analysis to the finite state machine? We need to reverse the effect of the algorithms from the Dragon book. So again, we have the tables, and what we do is we start from the starting node, and we want to visit all the other nodes in the compressed tables. And this is gonna allow us to recreate the original finite state machine. As you can see here, we don't have the enum anymore because this is from a binary, so we don't know the symbolic name of token type 2, but it's equivalent. Table decoding is a bit complicated, so I'm going to give a simplified version of it. So let's assume that you have a table which is called transition table that gives you the next state based on the current state and the input character. Okay, what you can do is this. So you have the states here, and here the current input character. If we start, for example, in the initial state of our graph, and we want to know what happens when the user types a D, or we have a file that starts with a D, we go into the table, look at the state number 1, which is this column, and we cross-reference it with the row relative to the current character, which is D. And what we find is that the next state is 2. And as you can see here, when you get an input D and you are in state 1, you reach state 2. Of course, this is a simplified version because, as I said, the tables are compressed using some tricky algorithms, but you can look at the code because there's not enough time for me to explain everything in detail. So now we have the final state machine and we want to recover the regular expression. A way to do it, and this is what we implemented, is this one. So we have many accepting states in our final state machine. But let's say we're interested only in the token, at this step, only the tokens of type 2. So we want to find all the ways that we can reach state 4 and 7 starting from 1. What you can do is take the other accepting states and make them non-accepting, so like this. Then what you can do is you reverse the edges of the graph, like this. And you start from the accepting state you care about and visit all the nodes you can reach. In this case, you only get the blue path that ends in the initial state, okay? You can then take this blue path, that generically speaking is a graph, and take it as a subgraph. So it's simpler to analyze. You can already see that it's pretty clear what this piece of final state machine does. Then from here, thanks to Kleen's theorem, we know that it's always possible to go from final state machine to a regular expression and back. So we apply some computer science algorithm from Hopcroft, another famous book, and we also apply some simplification passes to get a better looking regular expression. And you can see here, so we have an initial prefix which is constant and we need to have it. So you can see the first accepting state is after death and it's equivalent to this. And then we have an optional part here which is INE, and this is the second state. And so we have, if we repeat this for every accepting state, we get back all the different regular expressions. The final part is to generate valid tokens. And there are many ways to do it, but one of the simplest way, the most simple way, is to recursively generate valid substrings. So for example, if we have a regular expression that just matches the letter A, we are gonna return A. If we have a set of values, we can choose one character randomly. If we have either A or B, we can flip a coin and generate either from A or from B. If we have A then B, we can concatenate the result from the generation from A and from B, and so on. It's pretty simple. Okay, so demo time. So this is the example from the slides. You can see here the most interesting rule of the tree. And we're gonna build this file using a simple makefile, and this is going to give us in the end this object file. So what we're going to do is we load it into Ghidra and let it analyze YYLX basically. So you can see here we have, it's not as nice as the source code, but it's still quite recognizable. These are some tables. And of course, the script we are going to run now doesn't assume we have symbols. So the symbols are here just to make it easier to read. This is the main data flow extraction script. It takes some time, and then we have, okay, so this message tells us that it worked. Go back to the shell, and first of all, let's look at the extracted data flow. This is what it looks like. So you can see here, even for a simple definition file, it's quite complex. And this is because Ghidra doesn't optimize this intermediate representation very well. Okay, so now we're gonna try to see if we can find the tables using this wrapper script that runs the Java part of Reflex. And this is tmp out.xml is a GraphML file. So it's just the exported graph. And if it works, we get all the options we need to fit to the other scripts. So let's see what it does. This script takes the table and uncompresses them. And this is what we get. This is a bit different from the example I gave on the slide, but it's because Flex creates some implicit rules and some additional state that we don't care about. But we can run a simplification on it. This is the pickled version of the graph. Okay, so now we have the simplified version of the finite state machine. We can look at one of them. So this one is the finite state machine that we extracted, that it's relative to the fine rule. So there's an additional state that it's not important, but you can see here basically DEF reaches the first accepting state, and then we have another one for the optional I and E. Okay, so now let's recover the regex from this. This is done with this command. And you can see that we have a regular expression that's equivalent to the one I put on the slide. So they are the same, just written in a different way. And to generate valid tokens, we can use this other command, and we get a stream, an infinite stream of valid tokens. But now let's try with a more real-life example, like a Slate, which is the part of the C++ part of Ghidra. So now it's running Ghidra in headless mode, and it's gonna take some time to analyze the binary and then run our script to extract the data flow, and then automatically do everything I've done manually so far, but it's gonna do it all together. So we're gonna just get a valid stream of tokens out of this. So just let's wait a bit. Okay, so the analysis is done. Now it's running our script to export the data flow. This is the Python part. And these are valid tokens for this lake binary. And this is pretty much it. Key takeaway from this work. So we are able to identify flex table automatically. And then from the tables, we can extract the finite state machine and recover the regular expressions. And from the regular expressions, we can get valid tokens without running the target even once. However, of course, we have some limitation. The first one, and the main one, is that the Ghidra-based data flow analysis is not very reliable, because we're doing pattern matching on the data flow, and the data flow that Ghidra gives you changes a bit between, for example, different architectures. Of course, this only works for table-driven parsers, and the implementation is limited to Bison and Flex, even though this is just an implementation detail. You can apply the same idea to different table-based parsers. And yes, we don't yet handle the parsing part, just the tokenizer part. So you are not able to generate structured files with this approach yet. As future work, we want to find more Bison-based target. That's difficult to do because they are usually not advertised. So contact me if you have information. And then, yeah, we want to look at the parsing part. And an idea we have to improve on the data flow limitation, data flow analysis limitation, is to use the binary lifter that my company's created that gives you LLVM IR that you can feed into LLVM optimization passes and analysis. And they are very robust and gives you a consistent output. They also have this thing called a scalar evolution, which gives you information about table accesses, array accesses, and stride. So you already know the size of the tables without needing to do pattern matching, for example. Finally, we want to look at other parser generators. For example, NTLR is still kind of table-based, but it's more powerful than Bison. And yeah, we want to find bugs in closed source software. The code for the tool is available on GitHub, and feel free to open issues, ask me about it, fork it, and make pull requests. I'll be happy to merge them. And thank you very much. You can find my contact information on the corner in the bottom right. That's my email, my Twitter account, and my website. Thank you. I'm available in the chat for the questions.